Okay, so thanks of all. It's a pleasure to present a little of Bingo in this workshop, and I wanted to talk about the the Bingo project in general. And I am a Brazilian student. I am PhD student from the University of São Paulo, and I'd like to talk about the general information about the bingo, for instance, contextualize why we chose the 20 centimeters cosmology and why we chose intense mapping method. So I will show the preliminary information about the telescope and what will be the optical design and the current results for beam modeling. Of course, in 25 minutes, I won't be able to show all about the bingo, but that can be seen in our 7 papers recently published. And in advance, I'd like to say that I'm not a specialist in instrumentation and optical design, but I hope to give an overview. And Karin Fornazier will present part of the foregrounder move and 21 centimeters syllabus estimation tomorrow. So first of all, it's important to outline the reason for the 21 centimeters cosmology. CMB was very quickly measured by Planck, which provides the richest information from the universe, primordial universe, and also galaxy surveys like Sloan, DAS, among others, provide valuable information about the matter distribution in the local universe. Okay, but high neutral hydrogen emission can be complementary way to get information from the universe between those. For example, this expression represents 21 centimeters brightness temperature at Z redshift, and it can provide astrophysical and cosmological information like hydrogen ionization states, Hubble constant value, and even trace the matter distribution on large scale in the radio band. So Bingo is interested in epoch after reionization when main neutral hydrogen are inside dumped Lima alpha systems. Okay, but why intensity mapping method? Using 21 centimeters through the intensity mapping method arises as a promising way to map the sky. This method combines low angular resolution in a larger area of the sky cover in a faster time than galaxy surveys, for instance. And to understand the idea, we can look at this picture. We can take any region from the sky with various signal sources, and then we can divide this one into regions with resolution areas like these squares. All sources inside each squares will be contributed the same signal. In other words, our light source is seen as one source of the information. And it's interesting because we don't need to identify each source individually, and even weak sources contribute to the signal. So we don't need to resolve individual source, and even weak sources contribute. It's important. It's possible to cover very high Z. Also because it has a precise measure in the radial distance, the analyze our tomographic, what allows to build three-dimensional maps from the sky. However, like to CMB observation, one of the main problems is that the same frequency band, many other sources different from neutral hydrogen contribute to the same to the observation. But okay, but again, why 21 centimeter intense map? And I think baryonic acoustic oscillation is the main answer for it. We aim to get a statistical measure of the the BAO, mainly because neutral hydrogen traces the matter distribution, and it's possible to measure BAO, and with this we can put hard constraints on the dark sector, in dark matter in specifically. On the left, we can see we can look at a plot of the 21 centimeter angular power spectrum for both 0.13 and 0.45 redshift. Shows how BAO can appear in the appear in a 21 centimeters power spectrum like the Hope Bingo telescope. And one on the right, there's a classical representation of BAO in Fourier space. Okay, of course, Bingo is not only 21 centimeter intensive map project. There are a lot of others, but in this picture is Bingo is the only one that will operate in a single dish model here. And okay, a question now is, where will Bingo be? Here we can look at the South American map with Brazil in yellow, the state of São Paulo, where I live, and the state of Paraíba, where Bingo will be built. Specifically, Bingo will be built in a far and isolated small village inside this state called Aguiar. Aguiar is a small village with a population of about 6,000 people, and where there are many hills around it. And why this place? The site was selected after several analyses, such as tomographic and radio frequency interference. For instance, Mike Peel paper present this plot with radio frequency interference sensors of the site, and he showed our no cell phones or other detected signals down to the sensitivity of his sensory equipment. From an artistic perspective, Bingo will be like this, composed of 2 large mirrors and a focal plane with several feed horns, how we will see some. Great, but first it's essential to say the current aims and another possible extension in the near future. Again, the Bingo aims to use 21 centimeter post-reionization through the intensive mapping method to put constraint on the dark energy models and modify gravity and so on. But we have been analyzing 2 other possible extensions to study fast radio burst science and CAO cosmology, like the previous presentation. Okay, but general information about the Bingo. Bingo will be a fixed transit telescope covering a region in the sky by drift scan, like this. It will explore the South celestial hemisphere between -10 degrees and -25 degrees in declination, with 40 arc-minutes resolution, and between 900 H and 26 megahertz. So the telescope will be composed of 2 40 meters mirrors in a cross-intergonal design, where the primary reflector has a focal length of 40 meters, and the explanation is we need to have a clear beam, low side lobes level, and low cross polarization rejection. So for a good performance of the foreground removal process. And the horn is designed to be a conical conjugated in aluminum. The weight is about 800 kilograms, and there are a maximum diameter of 1.7 meters and a length of about 5 meters. It's interesting to say that inside this cage, the feed horn has a cart that allows it to go up and go down vertically and move back and move in forth. It's important to next slide. So what we needed to resolve until recently was to get a focal plane description. How many horns we will need and what localization those will need to be. The focal plane design needs to satisfy the scientific and instrumental requirements outlined in Richard Butt papers from 2013. I mean, for those requirements from the Butt's paper, we analyze in the bingo paper 3 the focal plane description and 4 possible designs, 4 possible arrangement of the horns. There was hexagonal model composed of 49 feed horns and with all horns fixed all the time. And then we analyze another 3 other models, another 3 other arrangement, change that it's possible each horn position changed by vertical movement each year. For instance, we can see rectangular design was designed with 33 horns, and each horn can move up to 42 centimeters upwards and downwards in 2 steps of 21 centimeters. Each new vertical position of the horn remains fixed for a year. And these other arrangements, double rectangular and triple rectangular, were designed not to have been overlapping the sky. That is, to eliminate the gaps in the sky coverage. And each horn can be moved to 30 centimeters upwards and down into steps of 15 centimeters. Double rectangular has 28 horns and triple rectangular has, I think, 36 horns. Okay, you use these 4 requirements in our study. And again, these requirements are necessary because of the strong foreground signals. Some of our results about the optical design published in our paper and a complementary paper with Carlos Wench. We have the results for the Stokes parameters for the double rectangular arrangement, where each Stokes parameter is summed up for all beams of this configuration, computed in 1100 megahertz. And we can look at the figure on the right, vertical and horizontal polarization for direct and cross measurements. As I said before, the plot on the left shows us that our horns have have side lobes low, above minus 25 dBA, and the cross polarization rejection is low too, above minus 20 dB or minus 30 dB. Also, they have a main beam closer to the Gaussian shape. Okay, and for choice, our arrangement for bingo phase one, we define one thing that we defined was a one-dimensional total intensity for the arrangement as in this equation, normalized by the intensity peak of the central horn. And our results were computed at 1,100 megahertz. And so we can see here the results of the double rectangular as close homogeneous as possible. And then in Vincenzo Riccardo paper from the bingo, Vincenzo papers for bingo shows sky over or covered uniformity achieved with the double rectangular. The plot shows the number of the observation per Helpix pixel, representing how the vertical displacements works regarding homogeneity. Offered choice, the arrangement, it's important to realize why the double rectangular was choice for satisfying all scientific and instrumental requirements, and because has a homogeneous coverage, and of course great cost benefit. So after establishing the bingo optical design configuration, we have been working both on mirror construction models and how this can change the bin shape. About the bin, also we have modeled the bin shapes using first Gaussian function and after Zernike polynomials. For the Gaussian function, we fit the bin near the central position on the focal plane. We could see that although the main bin is well fitted by Gaussian, the side lobes are not even if we have asymmetrical side lobes or just if we have side lobes. For instance, here we have grasp software output for bingo bin, and here we have a Gaussian fit and the residual between them. And here we have the same bin, but included side lobes, and we can see that it's the reconstructions don't work well using Gaussian model, of course. So we began to use Zernike polynomials to model our bins. And here we can see a symmetry bin and symmetry bin and asymmetry one expected to bingo in different places on the focal plane, using grasp software output for our expected bin, the first column, and using Zernike polynomials to fit them that. So we can see here that the residuals is low. Of course, they are smaller residual and better reconstruction here using Zernike polynomials to fit the bin. And the next work that will be publishing in soon, I think, João Barreto's work showed us that the more asymmetric bin was a better reconstruction than symmetric one. This effect is probably because Zernike has many coefficients that reconstruct the symmetric characteristic features of the bin. And for the final of this is a presentation, I just want to show you that bingo is more than science. I mean, the pure science. Our project has taken the scientific knowledge of the Agar village, and given several classes to help the local people understand about us, about more about astronomy and science in general. And in addition, it helps with more investment in institute for the village. And lastly, it's important to say when we hope to begin. We plan to start operating at the end of the next year, with in phase one, with 28 horns, with vertical displacement to cover an homogeneous part of the sky within 5 years. And Bingo telescope is made up of about the 120 peoples and estimated to be around $6-7 million. Our collaboration, and on behalf of Bingo, thanks so much.